Okay, the arrow. You can see. Okay. Oh, okay, so thank you very much for the nice introduction by Professor Lenenko. Thank you all of you for being here, listening to me, and to the organizers for giving me the possibility of being in this very nice place. It is an honor for me also to be the first speaker in this workshop. I'm feeling the pressure, but I will do my best. So I'm sorry because some of you probably already listened to a similar talk to me because I gave a couple of talks recently. But be patient because I really would like to give you with this talk what is my personal point of view on the topic of non-local in-time equations and the probabilistic approach. So I will not present one precise paper, but a sort of project which is in my mind. So since we want to speak about semi-Markov processes and non-local equations, we start from the very beginning, which is a very classical theory. Consider a family of bounded linear operators, say capital T, indexed by a parameter. Suppose they satisfy some assumption, like they maps one Banach space into itself, and they satisfies 1, 2, 3. So this family is said to form a semigroup, which is called a C0 semigroup. And if you define the operator capital A as in formula number 1 on its corresponding domain, then what we can say is that the mapping in formula number 3, so the evolution described by this semigroup, satisfy Cauchy problem, which is written down in formula number 4. But this is analysis. This is interesting in probability whenever we can say that this mapping, so the transformation induced by this operator, is just the expectation of some Markov process. Okay, so the representation 5 and 6 are true, and we can say that in this case, this transformation is the expectation conditionally to the starting point x, which represents in the Cauchy problem the vector variable of the Banach space of the position at time t of a Markov process. So when we can apply this theory, essentially in several situations, but we are always sure that we can use this theory when the Banach space is the space of continuous function vanishing at infinity. In this case, we have Feller theory. Okay, so we speak about Feller processes, which are strong Markov processes. And in this case, it is just very roughly sufficient to apply Reed's representation theorem and then the Kolmogorov procedure to see that you can always associate some kind of Markov process to a semigroup. So, but what it is usually, what we take for granted is the local behavior of the equation. So local means that, so essentially if you want to check if the equation holds for some t, then you need values of your function in an arbitrarily small neighbor of the point t. But in probability, local means Markov property. Markov property, so if you want to compute probability of some event in the future, then the only things that you need to take into account to compute this probability is the current position of the process. Okay, so this is Markov property. And this comes, of course, from the way the Markov processes are defined or constructed, but it comes from the lack of memory of the exponential distribution. And thus it comes from the exponential distribution of time intervals of Markov processes. Indeed, if you have any Feller processes, okay, we are speaking here about Feller processes, which are Markov processes and strong Markov processes in particular. We know that for any Feller process, if you define the random variable tau x, as in theorem 1, so the time the process leaves the current position, then this random variable must be an exponential, where exponential can mean 3 different things. If the parameter is just a finite number, the parameter lambda can depend on the current position. It can be a finite number. and thus we say that the position x is an holding point. So the process stays and then it moves away for an exponential time. Then you can have 0, so the process never leaves the current position x, or you can have infinity, and thus you have that the process leaves immediately the point x. But what it is another crucial property of Feller processes and strong Markov processes is that when a process stays in one position for an exponential time and it leaves away, it must jump away. It cannot leave continuously, because otherwise what happens is they lose the Markov property in that random time. So they lose strong Markov property. So this is the reason why Feller processes have this property. What happens is that essentially, if you want to imagine the path of a Feller process, you must take this kind of paths. So like a Markov chain, so a stepped process, a continuous process diffusion-like, or jumping process like Levy type, even with dense jumps. You can imagine very different kind of jumps, but you can combine. But what you will never see is a Feller process which is constant for an exponential time. You will never see a Markov process being constant for a non-exponential time. And you will never see a Feller process which is continuous and then which moves away continuously. Okay? So this means essentially why this cannot happen, in particular, why the exponential distribution is mandatory. Imagine that if you don't have an exponential time interval, so imagine that jumping process stays constant for a non-exponential time, and imagine that you condition to all the path up to the point S. Then what happens is that the information gamma of S is included in your information. Okay, you know all the paths, so you know that information, and you cannot ignore this information to compute probability of events in the future, because you can not use the lack of memory of the exponential distribution. So you are conditioning a random variable to be greater than something, so you cannot ignore this information. So one possible way to introduce semi-Markov processes, which essentially fill this gap and include Markov processes as a particular case, is to say that X is a semi-Markov process if it is Markovian together with this further information. This is not the only possible way. There are different approaches, but if you proceed in this way, what happens is that in this case, the renewal time, so the points where the process leaves its position becomes Markov times for the process. Okay, so our process have the Markov property in that point. This was the original idea by Levy to introduce semi-Markov processes. This probably you recognize something familiar here. Imagine that, okay, when the process is stepped, so these renewal times are just the points induced by, pasted by a sequence of random variables, like non-exponential random variables. Things are easy, but imagine that you have a strictly increasing pure jump process like a subordinator, so a strictly increasing Levy process, and you take the renewal points to be the range of the subordinator. That would be very interesting, and it is indeed very interesting. So what about, the question is, the point is, what about the PDA connection for these semi-Markov processes? That's the point, of course. The point is that they are related with non-local equations, so we have memory. Okay, so in the Markov case, we have no memory. The only crucial information is current position. Semi-Markov process, we have memory, we have non-local equation in time, but not only in time, but let's go in the appropriate order. So, of course, I don't have a general answer. I cannot say, given a semi-Markov process, what is its corresponding governing equation in the sense of the Kolmogorov equation like for Markov processes, but starting from the easy approach, so you start with a time change approach, I have some answers. And for example, the classical approach is to construct a semi-Markov process, making it a time change of a Markov process. So for this, we need a couple process, capital M and sigma, a Markov process. And the first coordinate is just arbitrary, essentially, an arbitrary Markov process. Take the second coordinate to be strictly increasing and jumping. Take the first passage time of the second coordinate, sigma, and then make the time change of the first coordinate through this inverse process, okay? It turns out that this is a semi-Markov process. The intuition is that, suppose this is just an example, suppose that this is a possible path of capital M and sigma. If sigma is strictly increasing and jumping, for example, and the jumps have arbitrary distribution, when you take the inverse of sigma, you get approaches, capital L, which are interval of constancy. With arbitrary distribution, because the distribution of the interval of constancy is induced by the distribution of the jump, okay? So you can put essentially anything. And further, if this sigma is strictly increasing, then the left inverse is continuous, as continuous trajectories, okay? So when you time change the approaches capital M with capital L, what you get is approaches with continuous trajectories, in this case, interval of constancy with arbitrary distribution, semi-Markov approaches. So now we take the expectation of the position of a semi-Markov approaches, and what happens is that this function here satisfies an local equation in time. What is this equation? Of course, even here we must make some assumption. The classical example is given by the case when capital M and sigma are independent and sigma is a driftless subordinator. Okay, you can include a drift, but in this case there is no drift. A subordinator is a strictly increasing Levy process. Its Laplace exponent is a Bernstein function with representation 18, and it turns out that they are governed by equation of the form 19, where the kernel in the convolution is given by the tail of the Levy measure, which appears in the Laplace exponent. So this is non-local, okay? So everything depends. So in order to see if the equation is true, you must come back to the value of the function q from 0 to t, okay? So this represents the memory in the evolution. Of course, if you take the Bernstein function to be the fractional power, and you compute the kernel, what happens is that that guy here is a fractional derivative. And it is possible to see using rule of calculus in several ways that this operator on the left-hand side is just can be interpreted as a Bernstein function of the first order derivative. Another very nice example is the case where capital M and sigma is an additive process. In this case, we are introducing dependence, okay? So capital M and sigma depends on each other. So when we make the time change, things are, of course, less easy. And in this case, in particular, sigma depends on capital M in the following sense. It is written, it passed through the Laplace exponent in formula 20, which essentially means heuristically that sigma behaves like a subordinator, but the Levy measure is parameterized by the position of the first coordinate. So it is just a subordinator locally whose jumps are determined by the position of the first coordinate. In this case, the governing equation is very close to the previous case, but there is x in the kernel. Okay, so in the kernel, there is the vector variable of the Banach space. This looks easy, but it introduces a lot of problems. Probably I forgot to say that A here and also A in the previous slide is the generator of the process capital M. Okay, sorry. And then there are other examples, even more general. For example, Hernandez, Kolokholtsov, and Tognazzi worked out a very general equation for very general capital M and sigma, less explicit but general using generators approach. Then there is a recent paper by Paty and Zrapion, and who worked out a self-similar case. So when there is a particular machinery using self-similarity, and the kernel of the convolution is the tail of the Levy measure of a subordinator, which is associated with the Lamperti transform with a stable subordinator. So this, you must be an expert in Levy process. But of course, the theory is incomplete because okay, I just told you some examples, but it is clear that the class of semi-Markov approaches, even the class of time-changed Markov approaches, is definitely bigger, and there are a lot of open problems in this. But my questions, which prevent me to sleep several times, was, but are we sure that we should really investigate investigate the equation for the marginal component of a process X if we could just add one coordinate and we fall back in the theory of Markov processes? My question is, yes, we should, but it took a lot of things to convince me that that I was on the right direction. What is the point? Of course, okay, speaking about probability, everything is interesting. Okay, so it is interesting. Also, the equation for the multidimensional. So also the equation for the couple X and gamma is, of course, an interesting problem which should be investigated. Unfortunately, I wasn't able to compute the generator of this couple process. It is a known information when the process X is stepped, so it is like a Markov chain with non-exponential waiting times. But in general, I don't know what is the generator. So speaking about probability is trivial. Also, speaking about analysis is quite easy, because if you can associate a process X with a time non-local equation, then with a probabilistic interpretation, you could give information on analytical properties of your equation. It could be interesting in numerical analysis. Okay, you can just make simulation of the process and approximate solutions and other approximation procedure. But it is really important also in statistical physics, in my opinion, because very roughly, I'm not a physicist. I usually say stupid things in physics, but very roughly, probability masses are proportion of particles, okay? And thus, if I work out with the position coordinate, so the position is the proportion of particle in one particular place, which is called in this slide the X, but which is something which I can observe instantaneously. What about gamma t? To know what is gamma t macroscopically is not an easy thing, and in any case, it is not observable instantaneously. Okay, you cannot take a picture of your phenomenon and observe gamma t. You must take care of the whole story of the system. So this is why I really believe this could be this is an important problem, even if we could add one coordinate and fall back in a known theory. But does semi-Markov memory implies non-local equation only in time? The answer is no. So I would like to give you just some flashes of insight on this possibility. For doing this, we should speak about random evolutions, which are a very abstract object. But we will speak about one particular example, clarifying example of random evolutions. So if the path of the process in the above part of the slide is a semi-Markov process, so with constant path, having a general non-exponential distribution, or also a Markov process, a Markov chain, if the distribution is exponential. This last process is a random evolution, which can be Markov or semi-Markov. Okay, so instead of nothing happen, instead of having something which, when nothing happened during a waiting time, which is called J1, J2, J3, in this last process, something happened. And what is happening here is just a translation at finite velocity. So this process here is called, just in physics, a transport process. Okay, it is also called a random flight. Essentially, it is the motion of a particle which moves at finite velocity. This is one example of random evolution, which are a very abstract object. So let's focus on this case. In the Markov case, so when the waiting times are exponential, you can interpret this the motion of this particle as the position of given by the integral of some velocity, in particular a Markov velocity. Imagine that you define as in formula 24 the velocity, so +1 and -1, which reverse velocity after exponential time. Just capital N, imagine that capital N is a Poisson process. Then take the integral, you integrate the velocity, you get position. So what you have in capital T is exactly this random evolution here. And capital T is sometimes called a telegraph process, okay? But in more than one dimension, things are more or less the same, but the velocity in RD is no more +1 -1 + C - C, but it is something on, if you are in R2, it's something in a circle. If you are in RD, it is something in a d-dimensional ball, okay? So if you want velocity be bounded, there is a d-dimensional ball with some radius, and then you take a Markov chain on this d-dimensional ball. You have a velocity, you integrate the velocity, you still get a position in RD. Okay, so it's just a bit more complicated, but the intuition is the same. And what happens is that this position capital T is not a Markov process, but if you take it with, if you add the information velocity, then this is a Markov process and it falls in the theory of Markov processes. And thus, if you define the expectation of the couple, capital T, capital V, this is a family of operators forming a semigroup, and they are generated by the equation in the operator in 27, which essentially means that the governing equation of this couple is the linear Boltzmann equation, okay, which is very popular in statistical physics. And we have the gradient part, which represents the free motion of the particle, and then we have perturbation of the motion given by this scattering operator. Scattering happens in the velocity, of course. So what my question is, what happens is instead of a Markov velocity, we take a semi-Markov velocity. The reason why this should be interesting is another, and is a different problem. I will leave this to physicists, and there are several physicists that during this week will speak about transport processes. They will be more convincing than me. I just want you to tell what happens to the Boltzmann equation when we put a particular semi-Markov process instead of Markov velocity. So let's decide to consider a semi-Markov velocity by making the time change procedure of a Markov velocity. So we use the theory as above. Okay, so we take Markov velocity, we time change with the inverse of the subordinator with some Laplace exponent, so the easy case, and we get a semi-Markov process. Then what happens is that this is the new Boltzmann equation. Of course, this operator f of d on dt minus v gradient x in this moment is a mystery. The definition is in the next page. But what happens is that imagine that there is no time change, so we come back to the previous case. So capital F disappear, you still get the Boltzmann equation. We are introducing this semi-Markov, so we are defining a new operator, which is the function of an operator acting in time and space. And what happens is that this is non-local in both time and space. Okay. How to define, this is the abstract definition. How to define the operator f of d on dt minus v gradient x. The abstract way is to use Bochner subordination method. Okay. In the next page, there is the explicit definition. Be patient. So this is just the operator capital U is just family of operators defining a semigroup on a suitable Banach space. You know that if you subordinate a semigroup, you define the operators calligraphic U as in 34, then this is again a semigroup, and the generator is the Bernstein function of the original generator. So it is sufficient to prove that the operator capital U was generated on a suitable function space by first order derivative minus v scalar gradient x, and you define Bernstein function of the original generator. But explicitly, instead of taking this as a Bochner integral, just take the Lebesgue integral representation of this operator here, you can write down it as in 36. And probably this is more familiar to people working in fractional calculus, because this is just like a Marchot fractional derivative. Okay. And of course, the prototype is the case when the Bernstein function is the fractional power and in one dimension, and thus this complicated guy just reduced to the fractional power of the material derivative, okay, which is called material derivative. So this operator here appeared in physics literature as a pseudo differential operator with Laplace and Fourier symbol. Okay, so this is not a new operator. Here it is just inserted in a particular theory. I think this is enough. Here is just a non-exhaustive list of references and specific papers that I considered in this talk. And thank you very much for your attention.
Thank you, Bruno. Bruno, any questions? Also, there is people who are not in this room, how to ask question for these people. There is a sorry, how to ask questions for people who are not in this room. Sorry. Okay. Sorry, how to ask questions?
The question from, is it from online?
Online, for instance. Or
they can unmute themselves and speak.
Unmute them. Okay, please unmute, introduce yourself and speak, who are online. Okay, so, okay.
And this time change, does it follow automatically that then the solution of this equation that you get with this fractional derivative in time and the generator of the process applied to the candidate solution can be represented as the expectation of this time change process, or are there conditions in order to have this stochastic representation of the solution, or it follows automatically from the construction of the process?
If I got the details of the questions, you mean you are asking to me if I take a non-local equation, it is automatically that the solution is the expectation of a Semi-Markov process? No, I did the contrary. I started with the expectation and I tried to find what is the governing equation. Okay, so in this approach, it is of course obvious because I'm trying to find an equation for the expectation. I'm not starting from an equation and finding the solution, the probabilistic representation to him. I use the converse approach. So in this case, of course, it is natural. Yes, this is the Cauchy problem. What I expressed to you in the slide is the Cauchy problem, but there is there are important results on also on boundary value problem. Essentially, the theory works in the classical case more or less as in the Markov process case. So if you take a bounded domain and if you kill your Semi-Markov process constructed in these ways on the boundary, then you have non-local Dirichlet. You have a non-local problem with Dirichlet condition, and if you reflect, then you have the reflected process on the boundary. But theory is still very incomplete in this case. Okay, so for example, when the boundary is not constant, and you take the non-local heat equation on a parabolic domain which is not constant in time, so which is time dependent, this is something on which I'm working on. Other more complicated boundary, there will be one of my colleagues presenting a talk on this, Professor Dovidio, which is an expert on this. And as far as I know, the theory is quite new in this case. So there are not much results.
Okay. Probably we have to start with next talk. Thank you very much, Bruno, for a nice presentation. And let me introduce the next speaker, Luisa Begin from University of Roma La Sapienza, of course, Italy. And everybody likes to visit this university, including myself, and visited many times. But she is specialist in, of course, non-local equations and fractional operators, different type of high-order equations. And actually, she introduced